I'm going to try to present a sort of a high-level overview of what's, in fact, two very large topics, AI and cybersecurity, and then a third big topic, which is how they interact. Um, so I'll be talking both about how AI can help in cybersecurity and also the cybersecurity risk of AI systems. Um, I always like to start with this video. Let me see if I can get it to play here. Whoops. I just did something horrible. Yeah. Yeah. There we go. There we go. So this was a video made for 60 Minutes, a U.S. news show. And it was about the office at DARPA that I used to work in. You're not hearing the audio, but that's okay. What you're going to see is an attack on a car. And the car is being driven by a 60 Minutes reporter, and that's my colleague, Kathleen Fisher, who was a DARPA program manager. What the remote attacker is doing here is turning the windshield wipers on, and then in a minute is about to disable the brakes. This is, we're not picking up the sound here, but it's okay. It's not very important. So let's just, this is the 60 Minutes reporter trying to explain to a general audience how the attack works, and you don't want to hear this. So now she's about to try to stop the car, and the brakes have been disabled. And eventually, of course, they let her stop the car. This is a second video. This is from an experiment that was done at Idaho Falls National Laboratory almost a decade ago, or maybe even a little bit more. And it was a carefully controlled setup to try to demonstrate that you could, by cyber means, disable a power generator. And again, how do I get this to go? There we go. Okay, here it goes. I thought it was running. There it is. Yeah, there's a little bit of dramatic sound going along with this. What's going on is the attacker has gotten through a firewall and is now controlling relays that connect this diesel generator to the grid. And what they're doing is turning the relays on and off out of phase with the power grid. And for those of you who know a little bit about electricity, you can realize that that's a very bad thing to do. This is what eventually happens. Yeah, so I show these both to just to make the point that when we're talking about cybersecurity, we often tend to think in terms of conventional information technology. But in fact, we've entered a world already where that's far from the truth, that largely we're now worried about things that interact with the physical world. A very cogent example of this that actually happened twice in December of 2015 and 16 was that Kiev was turned off. The power grid was turned off for a few hours in both cases, presumably by actors from Russia, but as is often the case, it's very hard to make a convincing case publicly about what we know about this. One of the things that was interesting about that particular attack is that although it was on operational technology, the bulk of the attack was actually conventional IT based. So the penetration was reasonably conventional. The privilege escalation was reasonably conventional. Once they had gotten to that point, they could now log into the system as legitimate users and then do a whole bunch of very ugly things, which included disabling the connections between the operator's consoles and the actual grid, turning off the relays that connected the grid to the rest of the city, the power generation, power transmission to the rest of the city, disabling the operator's console, and launching a denial of service attack on the telephone network all at the same time, which made it rather difficult for the operators to coordinate. The saving grace in this particular case was that the system is sufficiently old that there are manual switches they could send people out to throw. Often we tend to, as we modernize, in quotes, we often tend to remove those redundant, manually operated features, which in an operational world could mean that you are just totally screwed. Okay, let me say a few things by way of background. I worked at DARPA twice for a total of 6.5 years, and started a number of programs in the cybersecurity area. The next few slides come from when I was working there. They're part of a much larger presentation that was trying to put some analytical framework on looking at the whole cyber area. I've only picked a couple of slides out of this just to illustrate a point. What this one is showing is the growth of protective software, security software versus time on the upper axis, the one that looks like an exponential growth curve, and the size of malware in terms of individual exploit size, which is this flat line down at the bottom. Now, sophisticated attacks involve a number, maybe as many as a dozen different exploits. If you look at Stuxnet, that was about the right number. But each of those was about 100 lines of code. To be sure, very well crafted and carefully crafted code, nevertheless quite small, whereas the size of a unified threat management system deployed in an enterprise context is now in the size of hundreds of thousands of lines, many millions of lines of code. So we can quibble about the details here. The key thing to look at is that there's like 6 orders of magnitude difference in size between what the attacker has to engineer and what the defender engineers. Worse yet, this is from what's called an IAVA in the Defense Department in the US, which is sort of the operator's watch list for that month. So these are a report that says do these things. And notice that of the 13 or so things that are on this particular watch list, 6 of the vulnerabilities reported are in security software. That's even worse than it sounds, because security software often runs at a higher privilege level than user code. And so if you want to break into something, this is the best place to break in. So the summary of all of this, and there was a lot more in that report, the summary was that the US approach, and by that means everybody's approach, to cybersecurity is dominated by a strategy in which we layer security software on top of what's a very uniform but vulnerable architecture. By uniform, what I mean is that if you look at the number of operating systems we run in the world today, you can count them on less than one hand. And so if we find vulnerabilities, those vulnerabilities can be exploited on a massive scale. So that uniformity is itself an issue, but it's particularly an issue because the whole underpinnings of this entire infrastructure is very weak. Now, why are we doing something which on the surface of it seems sort of dumb? You take, this is the equivalent of building a castle on mud. The castle may have very strong walls, but it's going to sink anyway. And the answer is, well, we're here and we have to do something. And so what we're doing is trying to buy tactical breathing space. The analogy we often used was, well, if you fall off an ocean liner, you really do need to know how to tread water. But it's not going to do you a whole lot of good in the long run. So this is not what we're doing today. And by the way, by what I mean we're doing today is what's deployed. I'm not talking about, say, what Ava was just talking about. What we're doing today is not converging with the threat that's already evolved. So if you're in the middle of the fray, if you're fighting the war today, the view you typically have is that we have these very, very complicated computing systems out there that are so complex that it's impossible to design them without vulnerabilities. And if you hold that view, then you come to the conclusion that the best we can do is to try to manage our way through. And eventually we've come to a style of protection that, in a bit of satire on US government speak, I coined the term P4, for patch and pray perimeter protection, which is pretty much what we do today. So we try to put barriers around our systems, hope that that the bad guys don't get through. And then when they do get through, we try to, as quickly as possible, identify what went wrong, patch the systems, and pray that we've gotten to a better place than we were. This, in the long run, is a terrible solution. So, in contrast, I think the view we need to embrace is to recognize that we have inherited a legacy. And that legacy was based on the realities of computing nearly 50 years ago. So if you think about when was the first secure computing system project started, I'm probably forgetting some, but the thing I always go back to is the Multic system done at MIT. It's the reason I came to MIT originally, which was started in the late 60s and 70s, early 70s. It was done in an era where that machine was a large mainframe machine costing many millions of dollars that ran at 1 MIP, had less than a megaword of memory. So in that machine, it was a 36-bit machine, so less than a megaword of that. Disk drives were about the size of this table, held less than my watch does. So in that world, what we wound up with was Unix, which was the reaction to Multics, which was done on a very small machine. And the mindset that came out of that is that we had to develop a way of building systems that emphasized performance over everything. If you were trying to cram a lot of capability into a very small machine, you have to do a lot of things to get the performance out of that you want. And what we came out of that was the C programming language, which is a language that provides no protections whatever, and the Unix operating system, which was full of vulnerabilities. Now, it's a lot better than it once was, but the problem is that it's inherently architected wrong. So we're now in a position where, by almost any criterion you think about, performance, size of memory, size of secondary storage, everything is better by about a factor of 50,000 from when we started on Multics. And it just makes sense to re-architect and take advantage of all of that capability to build security from the ground up. A lot of my own research is in that context. In fact, I'm part of a hardware project right now that's trying to develop a new secure chip that is secure from the instruction set all the way up, that can enforce policies through a coprocessor that's looking at metadata attached to everything on the machine. I'm not going to talk about that because it's not about the theme here, which is AI, but I think it's important to realize that if we're going to deploy a lot more defensive technology with large AI systems, one of the things we have to constantly ask ourselves is, why is that not the target of the attack? Is there some way we can put at least that part of our system into a more privileged mode? Now, one way I like to think about the problem of what do we do after those protections fail is that this is really an economic trade-off. And if you think about what the attacker's doing, one way of characterizing this is what's called the cyber kill chain. And that involves a set of steps of reconnaissance, penetration, escalation, exploitation. That's the red line on the right, on the left. And that red line is, roughly speaking, value to the attacker versus time. This is all nominal. It's very hard to measure any of this accurately. And then the defender has a chain also, which involves detection, diagnosis, remediation, and regeneration, and ideally identification and punishment. So that's the green line on the right. And the total value to the attacker, again notionally, is the area under the curve. So the goal is to reduce that area. And you can do that by keeping attacks out through hardware, new software, and so on. You can reduce the degree of escalation that the attacker can get, and also increase the rate at which you detect and diagnose. And you can make it easier to recover. Now, all of those offer opportunities for AI technology, and I'll try to give a brief outline of where those things fit. But the point is that each of those is reducing the size of the curve. And hopefully you get to a point that looks something like this, where the value of attacking your system, at least, to the attacker isn't large enough to warrant the cost. finally, if you can actually identify the attacker and punish them, then there's a negative value to them, or at least an expected negative value. And so what you're really looking at is what is the net expected value to the attacker. So your systems don't have to be perfect. They do need to be good enough that that net expected value to the attacker is negative. If it is, then they won't attack you. They'll attack something else. Maybe they'll go back to robbing banks the old-fashioned way. So the goal then is, as much as possible, to keep attacks out, to detect them early, even to predict they're coming along, to be able to contain them as they're evolving, and then to rapidly bring your system back into full capability. And that last part is really the big pain point. There's a very illustrative example. When Saudi Aramco was compromised, their solution was to throw out all of their computers and buy new ones. Now, they do happen to be Saudi Aramco, so they could afford that. But they also made that choice based on the observation that they really had no certainty they were going to actually remediate the systems. So where does AI technology play in this? Well, first of all, let me give a brief background on AI. Because when you say AI, particularly today, everybody's thinking deep neural networks. And AI is a much larger field than that. That's sort of the shiny new toy on the block. AI technology developed mainly in two big waves. One that reached maturity in the late 80s, early 90s, and then the more recent phase with machine learning technologies. Earlier AI technology, which is the generation I grew up in, focused much more on reasoning than on perceiving or learning. The core of this was based on symbolic computation and representation of knowledge. So typically handcrafted knowledge, although to some minor degree, knowledge that was acquired through machine learning techniques. By the way, these are slides I borrowed from John Launchbury, who was a previous director of the office at DARPA that I used to work at. So in this older wave of AI, we typically built systems that were symbolic in character, focused on reasoning and explicit representation of knowledge. And those systems were capable of doing some quite spectacular things. One particularly focused on things like diagnosis and planning, things that modern wave machine learning AI is particularly bad at. So these are complementary waves of technology. Just a brief review, typically in its simplest form, what planning is about is representing pre and post conditions of operators, goal states and initial states of the world, and chaining together operators to get from the beginning state to your goal state. That sounds simple, but when you apply it to something like the following, this is a real example of an experimental system NASA did. This was led by my colleague Brian Williams, who's now at MIT. So this was something that was deployed on a deep space probe and could autonomously operate the system and diagnose and correct for things that went wrong. So this planning technology starts off saying, well, I want to get thrust, and one way I can do that is by planning to open these 6 valves. But what happens if one of the valves doesn't open? I need to be able to do mode analysis to figure out what state the system is actually in, and then based on that analysis come up with a complementary plan for remediation, which in this case involved opening a different set of valves. These are one-time valves that you don't want to open unless you really have to. So this kind of planning could take place in real time. Now, real time for a space probe is a lot slower than a lot of other real times. This happens in minutes, not seconds. But this was actually deployed. It actually worked. And this kind of technology is still quite valuable. We use it all over the place, and often in ways that people don't recognize as actually being used. Second wave AI, which is mainly from the late 90s forward, but particularly picking up in the last 5 to 10 years, this is what I tend to call computational statistics. So this is all based on very large data sets, typically labeled data sets, that are used for supervised learning, although there is also a whole cluster of techniques, pardon the pun, for unsupervised learning. In this style of AI, what happens is engineers create statistical models for specific purposes and then train them on big data. So the focus here is much more on perception. The place where this works well is if you want to build a perceptual system, not if you want to build a cognitive system that's doing reasoning and planning. Now, of course, in the real world, if you want an autonomous system, it needs to both perceive and plan. And so you need both sets of technologies. In the field of labs, we tend to treat these very much as opposites in conflict. They're not. They're covering different parts of the world. So the most recent development was the introduction of deep neural networks, which has more or less taken over this part of the world. There's a whole lot of technology here, which I am not expert on myself. The idea, though, is to create networks with very many layers. These are standardly, the idea is each layer is combining information, proposing nonlinear transformations on it, and essentially trying to separate planes within a high-dimensional manifold. Even neural networks are doing that, even though that's not the way they're often described. And the goal of that is to be able to classify things. The more we look forward in time, the more you start seeing these things having very distinct architectures that in many ways are trying to mirror, particularly for visual systems, trying to mirror what the human visual system looks like. So you have early layers that are feature identifiers, and then those are combined into higher level features and so on. And these systems have fairly spectacular performance. There's dozens and dozens of papers published every year on systems that train on, say, the ImageNet data set, get performance in, the accuracy above 97% or even higher, and that's all to the good. What I'm going to show you in a while is that it isn't quite as good as we think it is, particularly because these are open to adversarial attacks. So where do we deploy these kinds of technologies in the cybersecurity field? So one way I like to think about the problem is what our goal really is to identify entire classes of vulnerabilities, and then to devise a means to eliminate that class as a whole. So rather than looking for, say, every buffer overflow attack that happens and figuring out how to fix that, what we want to do is eliminate memory corruption attacks, or attacks based on identity compromises, or things that involve inserting components into your system that you didn't intend to be there. So if we devise architectural principles that eliminate all of these, then we've taken out all attacks of that kind. And that's what you want to do, because that's the efficient way to deal with systems. It may have a longer deployment route because these are not things typically you bolt onto an existing system. These are re-architecting of the systems. So to take a simple example of what I'm suggesting, if we think about identity compromises, that is, all of the attacks of phishing, password guessing, and so on, if we were to uniformly impose multi-factor authentication and biometrics and the whole class of things of that ilk, you take out that line of attack. And in today's world, that's the first line of attack. So if we can do that, we've eliminated a whole route that attackers get into our systems through. That doesn't mean they go away. It means they'll move somewhere else. And so then we have to think about another line of attack, such as corrupting inputs. These are, used to be the main line of attack. We've eliminated many of those, but basically you want to build systems that are memory safe and type safe. That involves probably switching programming languages for a very large amount of code. So that's going to take a long amount of time. And then there are a variety of things that mainly were enabled by the web. So these are various ways in which you can exploit scripting languages in order to insert components into your system that you didn't put there, that then wind up doing some of what they've been advertised to do and some other things as well. The other things being not so nice. So as I said, identity compromise is one of these areas where I think AI technology can play a big role. Using biometrics, face recognition, voice recognition, the mutual information between the two of those I remember many, many years ago, we had a large ubiquitous computing project called Project Oxygen at MIT. And one of the things we showed then on something that was sort of a progenitor of today's cell phone was a little system that looked at your lips and heard the voice and made sure that the lips and voice were the same and that they were the intended ones. So those technologies are well within reach on almost any system you look at today. That's one way of doing authentication. Obviously, we've deployed a lot of dual factor schemes in most enterprise organizations. We at MIT use a dual factor scheme for the core technologies. The rest of the place is wide open. And then another idea is active authentication. That is continuously checking that whoever is authenticated to the system is still the person using the system. And that's typically done by doing behavioral profiles and then checking that the operator is still acting within those. Now, what I want to talk about is sort of a big architecture picture. No one has actually built this. This is sort of my vision. And the idea here is that we want to build a system that can detect attacks, diagnose them, and recover from them. So it's at that second stage, what is the defender doing after the bad thing happens? And one way of doing this, at least the way I try to do it, is to couple a system with an architectural model of it. So you have the actual operating system and you have an abstract model of what that system is supposed to do. Think of it as an executable specification. And from that executable system model, we build a set of instrumentation that watches events going on in the actual application. So corresponding to any component in the system model, there is a certain procedure entry and exit points that represent the boundaries of that model of that module within the system model. And this instrumentation produces a steady stream of events that are signaled to the system model, which moves through its state changes in correspondence to what it's observing, and detects when the actual system does something that the system model doesn't sanction. So if it takes a control flow direction that it shouldn't have, if the data doesn't match the data flow specifications, if pre and post conditions of components in the system model aren't satisfied, then the system signals that there's a discrepancy, which initiates diagnosis. And diagnosis now consists of trying to think of alternative behavioral models for components in the system that would explain the discrepancy you've observed. This is a classic AI technique called model-based diagnosis. Now, in addition, you may have a library of attack plans. So these are attack plans. I'll show you later on quickly how these are generated. These are multi-stage attack plans. Again, think of something like Stuxnet or the Ukraine power grid attack. These are things that involve the whole set of stages to move through the infrastructure towards a target. If you have those, then as you gather evidence from all the different kinds of sensors you have, you can make estimates of how likely it is the attacker is moving through one of those kinds of multi-step plans, and then take proactive actions to prevent it from happening. Finally, given a diagnosis of what went wrong, which is typically a set of different answers with some probabilities attached, if you're trying to recover, or at least to weather the storm and keep going while things are not in completely good shape, you can make informed decisions about what resources to use and what to avoid. So roughly speaking, you want to use the best resources for the attack that are not likely to be compromised. I'm not going to talk about all of those parts of the story. I'm going to focus mainly on detection. And the problem is, and to be fair, this is a fairly old slide. This showed the performance of an intrusion detection system called SNORT, sort of the granddaddy of a lot of intrusion detection systems. False positives are these. The true positives are down here. That's sort of embarrassing. Today's systems do better, but the false positive rate is still quite high. And that's not good. So the root of the problem, in my view, is that the detection systems don't know what they're doing, basically. They don't know what the attacker's doing. They don't understand what they're defending. And there are reasons for that. So one way of looking at this is detection systems could fall into 4 categories. And you can break this up based on whether you're using statistical techniques or model-based techniques on the one dimension, and whether they're looking for deviations from good behavior or matches to known bad behavior. So let's go through those quickly. So if you're looking for matches to models of bad behavior, this is a classic signature recognition problem. It's what antivirus software looks like, most intrusion detection systems. They simply have patterns that match known bad things. The good thing about this is if this thing signals, you have good diagnostic resolution because you've actually matched something you knew about. The bad thing is it's completely retrospective. That is, it only catches things you've already seen and know about. And there's this knowledge cliff, so the attackers keep innovating and this thing doesn't keep up with them. So largely we've moved now into uses of AI techniques. So one of the older sides of this was the use of unsupervised machine learning to build statistical profiles of normal behavior. And the idea here is this is typically done by just collecting lots of data, clustering it, identifying the clusters that are considered normal and those that are considered abnormal. And when the behavior goes outside the normal clusters, you signal an alert. The good thing about this is that it's relatively easy to train, particularly in today's world of big data. You just collect a lot of data, you cluster it, and then you're there. And it's reasonably robust. You get some generalization, and it's reasonably stable. No matter how much the bad guys innovate, they typically fall outside the cluster of normal behavior. The problem is that it's not very informative. When this thing goes off, when you get an alarm, what it's telling you is something other than the normal behavior is happening. It's not very good at telling you what or why. And it also tends to have high false alarm rates. The thing that everybody is currently very excited about is the use of supervised machine learning. That is to say, having a large corpus of labeled data that you train against, and now what you're looking for is matches to known bad behavior again, or to generalizations from known bad behavior, because the learning process does generalize. So this is useful because, like the signature recognition systems, it's informative. When you get an alarm, you sort of know what's going on. And you get some generalization over the training set. This line here that says no manual engineering is really a lie. There's a lot of manual engineering that goes on in this in terms of selecting the data set, cleaning it up, and so on. The problems here are, particularly in the context of cyber, the problem is getting a good data set. We have lots of data. A lot of it is noisy. So if you're a telecom operator, for example, I have fairly close relationships with BT, for example. They have all the data in the world. They operate in 190 countries. They have data about all kinds of cyber attacks, but the data is very messy. And in addition, picking the features that your training attends to is a very difficult issue. For example, you might want to look at the entropy of something because it's indicative of compression and of use of cryptography. But recognizing that you want to do that is not necessarily particularly obvious until somebody mentions it. Finally, these things are spoofable. You can trick these systems in a couple of ways, and I'll show you a little bit about that in a couple of minutes. Now, the final piece here is where I do my own research, and this is the idea of doing model-based diagnosis. So the idea here is you have a system model, an executable specification in effect, that's used to monitor the execution of the system and to compare what the real system is doing to this executable specification as the system is running and to produce differences. So whenever the system does something that it's not sanctioned to do by the model, you then, well, what you really know is you either have a bug or an attack. Under the assumption that the system is in fact a faithful implementation of the model, then you know you have an attack. That assumption's a little bit strong, though. From the formal side, working with my colleague Taimur Minhas Khan, who's now at Surrey University in the UK, we did prove that the algorithm that does this comparison is correct, in that under the assumption the implementation is a faithful implementation, we showed that this algorithm would detect every deviation from behavior and would not false alarm. Now, the other thing that I think is useful to think about is how can we predict what would happen, and for that matter, what tools can we build for auditing our systems. And so this focuses on the idea of attack graph generation, which can be used for attack plan recognition. So at runtime, you can be trying to notice things that are indicative of an attack plan in evolution, and then to reconfigure in ways to prevent that before the target is really reached. You can also use this to audit a system by just asking the question of, given what I know about this system, how is it attackable? What could a bad guy do? Now, to do this, you need to have three things. So one is you need to have an accurate model of the system. The second is you need to understand a fair amount about how computing systems work. And the third is you have to have a model of how attackers think about attacking systems. So that's the picture. Descriptions of your infrastructure, knowledge about computing systems, and then, at least the way I captured this, is a set of if-then rules that talk about things an attacker might try to do. And this is done at a fairly abstract level. So things like something that says, well, if you want to control some component, find a way of affecting an input to that component. So it's sort of a chaining process of reasoning. And it was intended to mirror the way attackers think about things. You start thinking about what's my goal, and then how can I possibly get there? In our current system, we probably have about 100 of these rules. They include things like lateral motion, privilege escalation, life cycle attacks, that is, going back in the life cycle of the system and compromising it earlier on, and so on. These are just a whole bunch of the rules that are illustrative. When you then chain these rules together against some representation of the system, you can then come down to an attack like this. This is actually based on the Ukraine attack, which is get a user's password via phishing attack, log in as that user, download some malware like a keylogger and the kill disk tool, fill the disk in, force the sysadmin to log in, capture that with the keylogger, send that out to the bad guys, and now log in as the sysadmin, and then use that privilege to attack the ultimate target. So our system is capable of generating these attacks. And as I said, this can be used offline as an auditing tool. So you could ask, well, what could I do to make this not be a possible attack? And it can also be used online to detect things in evolution. Going back to the question of regeneration, how do you actually get your system back? I always like to point to this piece of work. This is a system done by Stephanie Forrest at University of New Mexico. This is using genetic programming, an AI technique, and it actually the final number on this was much higher, but the idea was that they could actually take systems that had bugs that were manifest and, given a regression test suite, could just mutate the software until those bugs went away at relatively low cost. So in summary, there are lots of opportunities for AI technologies to play in here. And I've listed a number of places where I think that they might be cogent. Let me just quickly talk about the other side of this is, okay, well, all this AI stuff's great. What about its vulnerabilities? So particularly, since I'm an old dog and came from the symbolic computing part of the world, let me pick on the other part of the world. This is, as people are probably pretty well aware, systems that showed very high accuracy in, say, recognizing images out of ImageNet can be fooled badly by just mutating those images a little bit. So here's something where you add some targeted distortion. I noticed that Ava's shirt sort of looked like this. And you add a little bit of that to this, and now this system that was pretty good at recognizing pandas is now absolutely convinced that this is a gibbon, which is from a whole different part of the animal kingdom. Here's a whole bunch of other examples. All these things over on the left that look like random dot patterns are recognized with high confidence as real things. All of these things, you can see the labels here, that's recognized as an electric guitar. this is recognized as a king penguin, and so on. Sometimes you can sort of guess why it's doing that, but not often. And then this one is one of my favorites. This is a 3D printed turtle. This was done by some people at MIT and some other people. So the person at MIT I know who was involved in this is Alexander Mondry, who is an expert on generative adversarial networks. And this turtle from any pose is recognized with very high confidence as being a rifle for reasons that are totally unclear to anybody. Now, to pick on other parts of these systems, this is a list of vulnerabilities discovered in a variety of, again, machine learning systems. But really the problem here is they all use a variety of image processing libraries, all of which have vulnerabilities. So one thing to remember is that a lot of this technology uses large and complicated systems, uses a lot of third-party stuff. That third-party stuff is always coming with some not so pleasant surprises. So this is true, by the way. I don't have a chart on this, but there's been work done on looking at older AI reasoning systems, and we have similar results on that. So in summary, I think the future for use of AI in cybersecurity is bright. There are a lot of opportunities. I was just trying to raise some cautions at the end about irrational exuberance, as was once said about the stock market. We have to be cautious, but there is a bright future here. My own view, and the view that DARPA is now pushing in the US, is that we need to move to a third wave of AI that doesn't regard this as a conflict between symbolic and statistical techniques, but is actually trying to unify these into systems that have some amount of common sense as well. A lot of these problems typically, you know, if the system had any amount of human common sense, the problems we're seeing would go away. But how to build common sense into a system is a wholly unclear problem at the moment. So with that, just a summary of what I've talked about. I think AI could be very useful for detection, diagnosis, reconfiguration, and regeneration. It can be a complement to more fundamental protective techniques that will never be completely perfect, but could be a lot better than they are today. And that I'd like to thank you all for having me here. It's my first time in Sweden.